So this is chapter 3, section 2, starting from slide 13, using white noise to build other time series models. So I'm going to start off with just a refresher from chapter 1 of why do we even need time series models. So we don't model just for the purpose of having a model, we model with some goal usually. And one goal here is that we want to make statistical tests, and statistical tests, whenever we use data to answer a statistical question, rely on having a model for the data. And the model is sometimes called the assumptions for the test, but those are really equivalent things. If our model's wrong, then any conclusions drawn from it may be wrong. And that's something that we saw in the context of linear regression. Maybe your estimates are okay, maybe your uncertainty estimates are wrong. Our error could be small and insignificant. It could be disastrous. That's something we want to investigate. And recall that time series data often have data where things collected close in time are more similar than an IID model would predict. And so you need to have models with this property. We've already started developing these. We've already defined a general ARMA model. Here we're going to just look a little bit more at the ARP autoregressive model. You'll get quite used to writing out these equations. The order P autoregressive model, ARP, has this form M1, where yn is linearly dependent on p previous lags, yn minus 1 through yn minus p, and then we add this white noise process epsilon n. And often we'll consider a Gaussian ARP model where epsilon n is Gaussian white noise process. This model is called a stochastic difference equation. It's a difference equation, also known as a recurrence relation, since each time point is specified recursively in terms of previous time points, and stochastic just means random. Now, when you have a difference equation, it's not quite specified. The solution isn't quite specified just by writing out the differences. You also need an initialization so that each successive difference has something to build on. And we have some choices how to set up initial values. One possibility would be to specify the first p values of y explicitly, and then the recursion would define all subsequent ones. You can also start defining the value of the process at negative time. Sometimes it makes sense even to think that the process did go off to minus infinity. You might not have seen it, but possibly it did, especially if it's stationary. Then it's shift invariant, so you can shift it back to minus infinity and define it there. If you do either choice 1 or 2, you can define these initial values either to be additional parameters in the model or to be random variables. Now, something interesting happens if you want your model to be strictly stationary. Then you have to initialize it in order to be stationary, right? Because you want stationarity implies shift invariance. And so it has to be that if you take your process and shift it back to the starting point, you get the same distribution. Okay, in our in the model we wrote down M1, if we want a stationary mean, then we better start with mean 0, and then that's going to be preserved by those equations. We can also think about what the initial variance would have to be stationary. We're going to think about that in the context of a very concrete Gaussian AR1 process, M2, where yn is 0.6 yn minus 1 plus epsilon n, and epsilon n is normal 0, 1. We're going to initialize with y1 is normal 0, variance 1.56. We'll see that is the stationary variance. And having a concrete example will also let us reinforce our understanding by simulation. Let's even do that first, right? This is a model we want to understand, and if we want to understand it, it seems like a real good idea to look at some sample paths, a range of sample paths generated from the model. There's different ways to do this, and one direct way is just to use the arima.sim function in R. Once you've learned to use it, you can draw samples from any ARIMA model, which is a generalization of ARMA model that you want to understand. It's often convenient to set the seed for the random number generator so that you can reproduce the same plot every time you run your code. Then you can try different values of the seed to generate different answers. Anyway, here I've just set the seed to 1, 2, 3, 4, 5, 6, 7, 8, 9. I could have set it to anything. And I've generated a simulation from the ARMA model with AR is 0.6, no MA component, SD equals 1, 100 time points. And here you get what comes out of this. And it's a time series. What can we say about it? Well, probably the first thing you might wonder about and be a little bit curious about is the fact that it doesn't seem to have constant mean, right? It looks like it might have a trend going on there. Does your intuition tell you these simulated data are evidence for a model with a linear trend? Mine would if I looked at that. And the eye looks for patterns in data, often finds them even when there's no strong statistical evidence. That's one of the main reasons we're doing tests. It's easy to see patterns in white noise. Dependence makes spurious patterns even more common because the dependence produces kind of clusters of similar results that the brain wants to interpret as a systematic trend rather than a random variation. Simulating different models with different seeds really helps train your intuition. You see the range of things that come about purely by chance. Now, I also want to discuss at this point the issue of writing your own code versus using a canned function like arima.sim. Arima.sim is a great function. Sometimes, how do you know you're using it right? How do you know it's doing the right thing? Have we really learned anything just by using somebody else's code? Well, those are all reasonable things to consider. And so the bottom line is, if it's reasonably easy for you to do so, it's really not a bad idea for you to write the code yourself. Well, the code to generate an AR1 model is really not that hard. Here some is. We set n is 100 time points. We want to generate a time series x. We initialize it at rnorm1. Rnorm in R is parameterized by the standard deviation rather than the variance, so we need to take the square root of 1.56. And then here I've just done a for loop which explicitly codes up the recursive definition of the AR1 process. And then we can plot what we get. It's kind of interesting when you also superimpose points generated by arima.sim. When I tried, I find I had to set a lag of 13 to make this work out. And when you do a lag of 13, the points perfectly superimpose. So how do you explain this? Well, You can pause the video if you want to ponder it, but I'll give you an answer. So arima.sim initializes by what's called a burn-in. Throwing away here the first 13 simulated time points. And what's going on here, this idea of burn-in, it's an idea that's used in simulation studies. The idea is you don't know how to start in the stationary distribution. We're going to find out that starting with variance 1.56 gets you straight to the stationary distribution, but R doesn't know how to work that out in general. And so it just starts somewhere else, probably 0, and runs the process for a little while, assuming that if you just run it for a while, it'll converge to its stationary state. Okay, so what are the advantages and disadvantages of using arima.sim over the direct simulation method? This is something you always have to think about when you're deciding whether to use statistical software or write it yourself. So arima.sim has already been written and debugged, and it would be I guess not too easy to write such a general function yourself. Now, coding up the special case of AR1 gives you understanding and helps check you know what arima.sim is doing. That's always the danger with statistical software, is that you just use it and it throws out a number at you and you have an imperfect understanding of what it's doing. Well, checking that in simple cases you can concretely check that it matches what you think it should do is the way around that. Here's an algebra exercise computing the autocovariance function for model M2. Now, well, I guess you're going to see me do some algebra. It's good to be able to algebraically manipulate these objects, and it's really a relatively standard exercise in manipulating variances. So let's just go for it. Suppose I want to calculate the variance of yn. Then I can write this as the variance of 0.6 yn minus 1 plus epsilon n. That's the definition of of yn, and then this is 0.6 squared, the variance of yn minus 1, plus 1.2 times the covariance of yn minus 1 with epsilon n. The variance of epsilon n, this is equal to 1. The covariance of yn minus 1 and epsilon n is equal to 0. And so for stationarity, I should have the variance of yn minus 1 is the variance of yn, which in the usual notation for autocovariance, this is going to be the autocovariance at lag 0. And so then I get gamma 0 is 0.6 squared gamma 0 plus 1. So gamma 0 is 1 over 1 minus 0.6 squared, which turns out to be 1.56. So that's where that number 1.56 came from. It's the stationary variance for this AR1 model. And now I can do a similar calculation for covariance. If I want to define gamma of h, that is going to be the covariance of yn plus h with yn. And now I'm going to consider the case h is bigger than 0, because I just considered the case h equals 0 before. If h is bigger than 0, then I'm going to write this as the covariance of 0.6 yn plus h minus 1 plus epsilon n plus h with yn. And then I'm going to expand the covariance. So this is 0.6, the covariance of yn plus h minus 1 with yn, plus the covariance of epsilon n plus h with yn. Because this is white noise, it's epsilon n plus h is independent of yn. So this thing is 0. And this thing here is exactly, by definition, gamma h minus 1. So I get gamma h is 0.6 gamma h minus 1, and this has solution gamma h is 0.6 to the h gamma 0, which is 0.6 to the h over times 1.56. Okay, that's the autocovariance function. We can do similar things with the MAQ moving average model. Here is the definition. Yn is epsilon n plus theta 1 epsilon n minus 1 up to plus theta q epsilon n minus q. Epsilon's a white noise process. And then to fully specify y1 through n, we need to know epsilon down to 1 minus q. So we might need, again, negative epsilon defined at negative time points in order to initialize. And then to simulate or work out a likelihood, something concrete, we need the distribution of these things. Oftentimes we'll have a Gaussian MAQ model where epsilon n is Gaussian white noise. In this model, we've really defined a mean zero moving average model. We could add in a mean, just like we could have with the autoregressive model we had before. Okay, and so let's look at a particular MA process, a Gaussian MA2 in model M4, where I have Yn is epsilon n plus 1.5 epsilon n minus 1 plus epsilon n minus 2. And then we can, we can simulate from it and see what we get, just like we did for the AR process. Okay, so here is a simulation two ways. First of all, using arima.sim, and second, doing a direct calculation. And again, we see that they match perfectly. And so we're fairly happy that we know what arima.sim is doing. It's doing the right thing. That'll give us confidence if we want to use arima.sim for more complicated models that we wouldn't want to code up ourselves. Okay, and if you really want to check they're identical, there's this all function. All x1 is identically equal to x2, just checks that they're all the same, and they are. Now, what's happened to our trend? So if we go back here, the MA process, I've used the same seed, the same driving white noise, and just like the AR process seemed to have a trend, here we also see some kind of evidence of trend. I mean, we know that the model, in fact, does not have trend. So anything we're seeing is just chance variation. But it does seem to be there. You might wonder whether it's there in the white noise that drives these processes. And so you can plot that white noise, and here it is, and you see that I don't think there's clear evidence. So it's really, this is an example where the extra dependence from combining the white noise either through a moving average or an AR dependence adds a sort of somehow tips the balance so that you see this slightly spurious evidence for a trend. Okay, we're going to keep going with a random walk model, but we're going to take a quick pause.